Hello everyone, we are going to present our research, bearing remaining useful life prediction and fault classification based on simplified fuzzy adaptive resonance theorem of neural network and discrete wavelet transform. This presentation will be delivered with following order. Bearing is one of major causes of engine failure, so its condition needs to be monitored using condition-based maintenance strategy. By planning when and what to do in maintenance activity, efficient maintenance activity can be achieved. One way to monitor bearing is through its vibration signal, but costly installation hinders CBM implementation. To minimize its cost, artificial neural network combined with vibration signal can be utilized to achieve one sensor and signal for all information. In vibration signal, suspected frequency band that contains the information needed can be problematic issue. To address this issue, we propose to utilize multi-level decomposition of discrete wavelet transform. In artificial neural network, how to train new training datasets can be problematic issue. New datasets is intended to add new knowledge without reconstruct prior knowledge. To address this issue, we propose to utilize incremental learning of simplified fuzzy adaptive resonance theorem of neural network. Combination of DWT and SFMNN is proposed to predict remaining useful life and malfunction location of bearing. For proposed method, there are two steps used in this research. One, building optimum SFMNN configuration, and two, implementation, which is intended to show the implementation of optimum SFMNN configuration. After vibration signal is obtained, next process is feature extraction. In feature extraction, two domains are used. One, time domain. Two, frequency domain. In time domain, four features was extracted. That is root mean square value, kurtosis value, RMS entropy estimation value, and average AC power of a signal which represented by variant in statistic. Before extracting features in frequency domain, discrete wavelet transform is utilized. Two-level decomposition is chosen since impact caused by malfunction has impulse characteristic. Three features are extracted here. 1. Average AC power of the decomposed signal in each subband. 2. Average AC power from the autocorrelated signal decomposition result in each subband. And 3. Envelope frequency in each subband. From feature extraction, a RMSE feature is utilized again to create category label. Category label is created by combining two types of label, that is label for predicting RUL and label for predicting malfunction type. Category label for predicting RUL is obtained by fitting RMSE with universal failure rate function. Then normalize the fitted RMSE from 0% to 100% and then divide the fitted RMSE into L categories. The percentage in fitted RMSE indicates degradation rate of bearing. Category label for predicting malfunction type is obtained from reference about what malfunction type and when it happened. And then integrated category label is obtained by combining both labels above. Next, we configure the SFMNN by using extracted feature as input and integrated category label as output. Training process is conducted afterward to get SFMNN configuration. Sensitivity analysis was intended to obtain optimum configuration of SFMNN by observing the weight component connected to the SFMNN input component. The significance of the weight component is calculated by means of the average value for each weight component for all weight vectors in the weight set. Thus, it is apparent that there is a direct relationship between the number of input components and the number of weight components. Components with small weight value will be candidate to be removed. After getting the optimal SFMNN configuration, repeat all those steps in implementation step until SFMNN classification. SFMNN only produce degradation rate estimation and malfunction type. We need to convert the degradation rate into remaining useful life in the time unit. Smoothing algorithm aim to bring back the continuous characteristic after being discretized in SFMNN and produce RUL by extrapolating between current and previous degradation rate. Voting algorithm aim to minimize prediction error by comparing current initial result with its two previous result. Next, in experimental result, the study utilized the bearing dataset from intelligence maintenance system. Not all datasets are used, only selected one which contain information about malfunction type. After getting the feature that we want, next step is category label creation. In category label creation, data regarding RMSCE value will be fitted measurement with universal failure rate function, and then the fitted graph shown in red line in graph after being normalized into 0% to 100% will be divided into 7 categories, and the result of labeling is defined by RUL label. And category label creation for malfunction type is based on Miltiades and Ali research to know when the malfunction starts happening. After both category label are constructed, label integration is conducted and the result as follows. After all input features and category label for training are ready, the next step is training the SFIMNN. Configuration of SFIMNN is based on features extracted and integrated label constructed. And training results shows that the neural network create many node outputs in no faulty condition. This is because several different patterns that non-faulty bearing have, from one bearing to another. But these various conditions are represented by one category. It shows that incremental learning characteristic is well exploited for new pattern that show the same condition. Next, we need to validate the trained SFMNN using test data in classification step. Table shows that the model has a fairly good performance in the classification of bearing with inner race and roller element malfunction. But for the outer race fault, the SFIMNN model works well at the beginning and the end of the cycle of bearing operation. High overall classification accuracy shows that the initial configuration works well. Next, let's see whether SFIMNN's performance can be improved. Sensitivity analysis is conducted by pruning the components that have less significant weak value. Weak value graphs show that the input components number 12, 13, 14, and 15 have less significant value, so we propose to prune them, so that the final configuration of SFIMNN as shown. After we get optimum SFIMNN configuration, we go to implementation step and repeat step from feature extraction to training SFIMNN. From table, it is observable that the number of nodes is fewer because the input pattern examined by the SFMNN are reduced due to fewer input nodes. After training process, we will validate our model by classification step. From classification result, it shows that the overall classification is higher than the initial model. The improvement in final model indicates that there are some input components that cause a misleading effect. The model becomes more accurate when such components are removed. The graph in right side shows the sensitivity analysis result for final SFIMN and configuration. The weak value are more uniform than initial configuration. Result from classification process can be used directly. We need to convert them into RUL estimation and malfunction type via smoothing and voting algorithm. For smoothing algorithm result, there is a difference in the percentage of degradation rate of the healthy condition bearing. The actual percentage degradation rate is between 30 and 14%, while the model force degradation rate is to 0%. If model predicted bearing in healthy condition, while in ID bearing for fluctuation happens because SFIMN's misclassification as the condition is similar with malfunction starting time in ID6, but smoothing algorithm has another good function that is capable to compensate for this error. In right side is numerical example about how to estimate RUL using extrapolation in smoothing algorithm. Although there is difference between estimation and actual, the difference is small enough compared to the life of the bearing, and in practical application, maintenance activity rarely happen near life and a component, except the stakeholder choose corrective maintenance strategy. In conclusion, the final SFIMNN model was able to classify the input categories well due to the overall level of accuracy of the classification results was above 90%. A smoothing and voting algorithm is proposed to improve the prediction results of the remaining life of use and the result of classification of malfunction. And exploration of features that can improve the accuracy of the SFMNN model, such as bearing temperature operation condition, are recommended. The use of run to failure test data with the criteria of one bearing ID derived from at least one bearing can be suggestion for further research. This is the reference for this research. Thank you.